in NPJ biofilms and microbiomes about the microbiota alterations and antimicrobial resistance gene acquisition during intercontinental travel. Now, intercontinental travel has again increased substantially over recent decades, especially with the strong resurgence now following the decline, of course, during the COVID-19 pandemic. However, this also exposes travelers to the unfamiliar microbes, environments, and also dietary patterns that in turn may influence the gut microbiota. At the same time, travel is increasingly also recognized as an important driver of antimicrobial resistance dissemination, AMR, as travelers may also acquire resistant bacteria or resistant genes abroad and transport them back home. Now, several previous studies, including work from our own group, have investigated travel-associated changes in gut microbiota, but also AMR. However, most studies relied on pre- and post-travel sampling, so here, therefore, potentially overlooking rapid microbiota fluctuations and short-term AMR dynamics during travel. And to address this, we apply a more high-frequency daily sampling approach to capture temporal changes in much greater detail. We conducted a prospective cohort study involving 11 Dutch travelers visiting various countries in Asia. Fecal swabs were collected before, during, and after travel, and we also had some access to fecal samples before and after travel. With daily sampling of fecal swabs during travel whenever defecation occurred. None of the participants used antibiotics during the study period. Now, for microbiota profiling, we performed 6NS rRNA gene sequencing, while antimicrobial resistance genes were assessed using qPCR targeting the qnrB, qnrS, quinolone resistance, and CTX-M for the extended spectrum beta-lactamase. Now, these targets were selected based on our previous work from our group, which demonstrated the high acquisition rates of these genes in Dutch travelers, especially visiting Asia. Now, among the 11 participants, the median age was 37 years, ranging from 7 to 51 years. The cohort itself consists of 6 females and 5 males, with a median travel duration of 18 days, ranging from 5 to 23 days. We first investigated how travel influenced the gut microbial diversity over time. This plot depicts the Shannon diversity for each individual sample, with samples of each traveler colored here differently. And overall, we observed a transient decrease in Shannon diversity, especially shortly after arrival, and again after their returning home, after which the diversity then generally recovered towards the baseline levels, so pre-travel. Now then, to determine whether these observed fluctuations actually reflected consistent travel-associated effects at the population level, we next modeled the microbial diversity changes across the different travel periods by assessing the pairwise differences in Shannon diversity between samples and also within each individual period, and modeling done through mixed effects modeling. Now, despite the transient decrease observed in several individuals, no significant population level differences were detected between pre, during, and post-travel periods after post-hoc analysis. Instead, we observed quite strong inter-individual variability, which this suggests that there's highly personalized microbiota responses to travel. We next investigated the overall microbial community composition, here displayed a PCA analysis of beta diversity, with the different travelers depicted here also in the same different colors. Here we see that samples from the same traveler cluster closely together, indicating that the interpersonal microbiota differences were larger than the average effect of travel itself. And this is further illustrated by the circular bar plot here, alongside the PCA. So here the outer layer indicates the individual traveler from whom each sample originated. And this highlights that each participant maintained a distinct and individualized microbiota signature over time. And then we next investigated the overall microbial community within individual microbiota instability using the age distance between consecutive samples. Again, here a strong inter-individual variability. However, we also found that day-to-day compositional dissimilarity was significantly higher during travel compared to both pre- and post-travel periods, indicating that the gut microbiota composition became considerably more dynamic and unstable during travel. And interestingly, post-travel samples still showed greater variability compared with the pre-travel baseline, again suggesting that the gut microbiota may require time to fully recover after travel. And to illustrate these dynamics, we highlight here a single participant who went backpacking through Malaysia. And this traveler showed clear separation between pre, during, and post-travel samples in the PCA plot. And before travel, the microbiota diversity here and community structure appeared relatively stable, with low dissimilarity between consecutive samples. Now, during travel, however, the Shannon diversity here showed much greater temporal variability, including several transient decreases followed by recovery towards baseline levels. But in parallel, you see here transient fluctuations in taxa such as Bacteroides and Akkermansia already in a couple days during travel, showing really the marked day-to-day variability during travel before then gradually returning towards baseline after travel. Which brings us now to the next part, because we previously also saw AMR acquisition in these travelers in the previous plot. Here we focus on the AMR dynamics and resistance gene acquisition during travel. In this figure, the squares represent the fecal swabs and circle the fecal stool samples, with red indicating the ARG positive samples and gray indicating negative samples. Black squares representing the missing time points, but these are mostly due to no defecation occurring rather than really missed collection. Here we see the pre-travel ARG was nearly absent across the cohort. However, during travel, every participant acquired at least one of these targeted ARGs. Acquisition often occurred very rapidly, sometimes within only 1 or 2 days after arrival. But most notably, the qnrS gene here was detected in all travelers during travel, while the majority also acquired qnrB and also CTX-M, beta-lactamase genes, were newly detected in travel samples, at least in more than half of the participants. And also some ARGs persisted long after travel returned home, sometimes up to 3 months post-travel. And lastly, we investigated the microbial trends associated with AMR dynamics. We observed here a significant increase in Enterobacterales abundance during travel, which is in order including bacteria such as E. coli and Klebsiella pneumonia. And this increase really closely coincided with the ARG detection, which then gradually declined after returning home. These findings highlight the sort of transient microbiota dynamics that are often missed by traditional pre- and post-travel sampling designs. For the key takeaways, we highlight the value of daily sampling again. So traditional pre- and post-travel may miss many of the transient microbial fluctuations observed here during travel, such as the notable increase in Enterobacterales. And even short visits to high-risk environment pose a substantial risk for AMR gene uptake. And lastly, the first week post-arrival here represents a quite critical window for microbial shifts and AMR gene acquisition. And this brings me to the end of my presentation. I would like to thank all the collaborators involved here and the participants also involved in the study. And thank you also for your attention.